Hi, I'm Robert Chimenti, Marketing Manager at B&W Tech, and we're here at Photonics West today, 2012, to talk about some of our miniature spectrometers. What we have here is our Glacier X. This is the smallest TE-cooled spectrometer available on the market, and we're currently measuring the fluorescence from these 3 quantum dots. So we have fluorescing in green, red, and orange, and that's being pumped by one of B&W Tech's pulse xenon lamps. And then we're using the trifurcated fibers to measure the fluorescence into the spectrometer. And as you can see on the spectral readout over here, you can very clearly differentiate all 3 peaks of the spectrometer. The TE-cooled spectrometer is ideal for fluorescence because the low dark counts allows you to integrate for longer periods of time. Fluorescence is typically considered a low light level application, and therefore longer integration times are generally preferred. We also have on the screen next to this, we are measuring the absorbance of this green dot here going into the Quest X spectrometer, which is a room temperature spectrometer. And as you can see to the spectrum on the left, this is very transmissive in the visible and the near IR. And then as you approach the UV, it exponentially starts absorbing. This makes sense because when you're thinking of a fluorescent material, you want it to be able to absorb the high energy photons and you want it to be able to emit the lower energy photons. So this is a very typical spectrum that you could expect from a quantum dot. Over here we have our SOL 1.7 NIR spectrometer. It's a TE-cooled InGaAs linear array spectrometer. And what we're showing in this experiment is transmission. So we've already shown a fluorescence measurement, we've shown an absorbance measurement, and here's a third type of measurement you can make with a B&W Tech spectrometer. So what we have here is we have a B&W Tech tungsten halogen light source. It's fiber coupled into this cuvette holder, similar to the cuvettes that we were using before. And inside of this right now we have varying samples. So for example, we have a cuvette full of water here. So you can see it looks very clear and transmissive in the visible, but when we look at it through the near IR, we can see that it is very little transmittance in the near IR region. Opposite, we can take a look at this vegetable oil, which looks much more opaque than the clear water. But when we put this into the spectrometer and we look at the transmission in the near IR, we can see it's very high transmission levels in the near IR. One other thing that is interesting to look at is we look at the water again, and we take a measurement here, and then in this cuvette I have gin. Now gin is mostly water, also has ethanol and sugars in it, and we can see that when we put this in and we take a measurement, that it's a very similar spectrum to that of water, but you can see subtle differences between the water spectrum and the gin spectrum. So NIR spectroscopy allows you to identify differences in molecular structure of a material. You can identify contaminants. So if you're looking for pollution, as we can see here, once you get the alcohol in there, it slightly changes your spectrum. It can tell that for other contaminants. And for more information, please visit our website at www.bwtech.com.